Hello everyone, welcome to chapter 4 of the finite element method. In this video, we are going to look at how we can solve the plane trusses problem using finite element method. Before we look into the detail of how we can solve this truss structural problem using finite element, I think it is very important for us to understand what is truss structures and also how does this structure looks like physically. A truss is a static structure consisting of straight slender members interconnected at joint to form a triangular units. So it means here we have a slender members which is a structure that has the length which is longer or bigger in terms of the dimensions as compared to its diameter, or what we call it as the L over D, which is greater than 1, or in other words we can say that the length of the structure is far bigger than its diameter. So to make one truss, then we have to actually connect these truss a single slender elements here with another elements to form a triangle units. So now we have 1, 2, and 3 slender members to make one triangles unit here. There are two types of trusses, which is known as the pitch truss or common truss, and also there is another type of truss structure which is known as the parallel chord or flat truss. So these pitch trusses and parallel chord, they are different, characterized by geometry and also their applications. This is one example of the pitch truss structure, where as we can see here, this kind of structure is actually connected between the bigger cylinders or tube or hollow bar with the smaller diameters cylinders to make a triangles or several triangles, and to make this whole structure as we have in these figures. So the pitch truss structure also or commonly used or commonly found used for the bridge constructions. So if we are going to the rural area, so we can find this kind of structure which is very famous for the constructions of the rail tracks for crossing the rivers or the valley. Now let's look at the plane trusses model as shown in these figures. So these plane trusses actually comprises of two force members which are interconnected at their frictionless joint. So now if we take this example, the joint that is connected all the slender members here is assumed as the frictionless joints. So that means they are rigidly connected at each nodes or nodal points. All loads, including the external loads and also the calculated reaction forces due to these external loads, are only applied at the joints only. So that's mean here for dealing with the plane trusses, all the external forces or loads and also the variations will only apply on these joints only. That means there will be no force or a load that apply on the elements or within these elements. There are two displacement components at each nodal points or at a given joints or nodes J as shown in this figure. So this is also this two displacement is also called as the two degree of freedom. So that's mean here if we are actually working on the x and y plane, and then if I take one nodes or joint any joint on these structures, so at one nodal point or at one joint there will be 2 degrees of freedoms. That means this joint here is free to move in x directions and also in the y directions according to these 2 degrees of freedoms. Now let's introduce the local and global coordinate systems. The global coordinate system usually used to represent the whole system or the whole structure that we are going to analyze it, while the local coordinate system usually apply locally on each elements. So if we take one truss elements as shown here, so if I just take this element here, then I enlarge it so that we will have the one that's shown in the slide here, which is we have a slender members and it is connected at two nodal points 1 and 2, which is this member here. If we view it locally, then we can actually write its own coordinate systems or local coordinate system, which is spanning along these members. And as shown in this slide here, it start from nodes number 1 along these members, and we can call this axis as the local axis, and it's given by x prime. But if we look the whole this structure, if we look this structure as the whole pictures, so we can view this in the x and y direction, for example, where we have our global coordinate system, which has their axes x and y as shown in these figures. And when we have defined the global coordinate system and also the local coordinate system as shown here, then we can start to relate these two coordinate systems from the local to the global, and we can do the translation as well from the global to the local coordinate systems. So if we view these elements of our truss locally, then we can have the displacements is similar to the one that we solved in the 1D bar problem, where we will have Q1 and then we will have Q2. That means the displacements of this particular point locally in x directions, we have Q1 prime, and the displacements of this particular point number 2 following this local coordinate system S1, then we will have Q2 prime. But if we look at these structures in the global coordinate system, then we can imagine that this structure has 2 degrees of freedom at each another point in such a way that we can write these displacements following the sign convention that we have before: Q1, Q2, Q3, and Q4. So this is what is explained here. So in the local coordinate system, the displacement only have 2, similar to the one that we deal with the 1D bar problem. So we have Q1 prime and Q2 prime. So this is just to refer to the local coordinate system. While in the global coordinate system, we have Q1, Q2, Q3, and Q4. So in this slide here is actually to shows that the local coordinate systems and global coordinate systems, they are interrelated, which is we can do the translations or transformations from the local coordinate systems into the global coordinate system, and we can do the transformations from the global coordinate system into the local coordinate system as well. So let we consider a truss member which is initially at the rest, as shown by figures A here. Then this truss is actually under external load applied to this structure. It will somehow deform in such a way that it's from the rest here, or initial conditions there, and now it's somehow move slightly to the left and slightly upward, as shown by figures B there. So the translations in the x directions at each another point, 1 and 2, is given by Q1, and then it slightly translate upwards, and it is given by Q2. Similarly applied at this point number 2. So initially this initial point of nodes number 2, then it translate to these new positions after the loads external load applied to this structure or to the system. So if we project this displacement Q1 normal to the structure in the initial conditions, then we will find that this displacement Q1 is actually equivalent to the Q1 cos theta. So this is referred to these small portions of the displacements contributed from this Q1. Similarly for the Q2, then if we project this to this structure in the initial positions, then we will find that these the amount of Q2, which is, if we view this in the local coordinate system, is equivalent to the Q2 sine theta. So how can we get this value? To obtain the equivalent displacements of Q2 in the local coordinate systems, what we can do is by taking the trigonometric process or rules in order to obtain the equivalence value between the global and the local coordinate system. So this is our Q Q2, and then considering that we have the similar angle here theta, which is we can take this, the angle theta here is actually equivalent to the theta over there as well. And then if we project these along the axis along this, if we project the axis along these cylinder members, then we found that the Q2, which is if we view in this coordinate system, is actually equivalent to the Q2 sine theta, which is actually will give us the distance or displacement that is equivalent to this portion there. And if we take this Q1 cos theta plus Q2 cos theta, then this is the whole displacement here actually represent the displacements contributed by nodes number 1 as we view this in the local coordinate system. We apply the similar process to the nodes number 2 in order to obtain the relations between the global and local coordinate systems. Then we will find that the Q1 is actually equal to Q1 prime is actually equal to Q1 cos theta plus Q2 sin theta, and Q2 prime equal to Q3 cos theta plus Q4 cos theta. So to eliminate the theta term from the previous equation, then we introduce the new variable which is called L, which is will take cos theta, and we have another variable M, which is will take sin theta. So by having this new variable introduced, then we can rewrite the relation between the displacements in the local coordinates and the displacement in the global coordinate system can be written as functions of L and M. Then we will have Q1 prime equal to Q1L plus Q2M, Q2 prime equal to QL3L plus Q4M. Or in another name, we can write this as Q1 L plus Q2M plus Q3 0 plus Q4 0 for nodes number 1. And for the nodes number 2, we have Q1 0 plus Q2 0 plus Q3 L plus Q4 M, which this equation can be written in a more complex formats or in a metric format as shown at the bottom of this slide here. So the relations of the displacements in the local and the global coordinate system can further be simplified by introducing the matrix L here, which is this matrix L is actually called the transformation matrix, and it only takes these coefficients or value from the cos theta and sin theta of our elements. So that's mean here when we are dealing with the plane trusses, the inclinations angle of our elements is very important and have to be considered accordingly. For every structure that we have, usually we will know their coordinate system of each another point. So for example, at nodes number 1, we know the coordinates at nodes number 1, which is given by x1, y1. And for the nodes number 2, we have these positions in both x and y, which is given by x2, y2. So our purpose here is to determine the angle theta of our elements here, and also their length. So by using the simple trigonometry relations, then for the figure that we have here, then we can build the expression for the cos theta, which is given by x2 minus x1 divided by the length of our element. So L is actually measured from nodes number 1 until nodes number 2. For sine theta, which is we take the vertical distance of our elements, then divide by the total length of our element itself. Then the length of the elements can be obtained by taking the square root of the distance from 2 points in x directions square plus the distance in the y direction square. So this will bring us the length or the exact length of our elements as we measures along it. Alright, in this slide here, we are going to look at how we can come out with the element stiffness matrix for the plane trusses problem, which will be derived using potential energy equations. So a truss element is a one-dimensional bar element when it is viewed in the local coordinate systems. So if we can remember one plane truss which is in this triangle forms will be viewed in the global coordinate and also in the local coordinate systems x primes. So if we just look at a single elements or any particular elements in the local coordinate system, so we can view this similar to the problem that we solve based on the 1D bar elements. Thus, the element stiffness metric for a truss element viewed in local coordinate system can also be viewed, or in terms of its element stiffness metric can also be viewed similar to the 1D bar problem, and it's given by these equations. Then the internal energy in the truss element in local coordinate system, which is obtained from the potential energy equation, can be given by this equation, but the term for the displacement Q and then the element stiffness matrix in these equations is actually written in the local coordinate system. But for a truss problem, we when we solve the whole system, we will also view the whole system in the global coordinate systems. Thus, it is important to do the transformation from the local to the global coordinate systems for the displacement, as we can see here, so that the internal strain energy equations can be written in the global coordinate systems. Once we have done the transformation from the local coordinate system into the global coordinate systems, then the internal strains energy of the potential energy equations, which can be written in the global coordinate system as shown by the first equations in our slide here. Then it says here, since internal strain energy is independent of coordinate systems, whether it is in the global or in the local coordinate systems, as the element stiffness metric for the truss in the global coordinate system can be obtained by taking this the multiplication from the matrix transformations transpose multiplied by the element stiffness metric for the truss in the local coordinate system, then multiplied by the transformations matrix again. So if we expand this, the L transpose K prime truss and L, then we can actually write the similar equations in this slide here. And if we do the multiplications of these all three matrices, then finally, so we can rewrite the global element stiffness metric for a truss elements, which is given by the square of 4 by 4 matrix and multiplied by the geometrical parameters and also the materials parameters from the structures, where as we can see here our matrix K in global, which is depends on the L and M, which is, if we can remember, L equal to cos angle theta of our element, and S is equal to the sine theta of our element. So considering this is our element from point 1 to point number 2, so we take the angle from the horizontal line or axis here, and then we obtain the angle theta. So the L and S here, which is referred to the cos and sine of this angle theta. Thus, the system of linear equations in the form of KQ equal to F for one truss elements written in the global coordinate system can be written as this equation that we have at the bottom of the slide. This is by taking into considerations where at each nodal point, nodes 1 and nodes 2. So this is what we get here for one particular element. Then we have 4 displacements, which is represented the displacement at 2 nodal points, in this case point 1 and point number 2. The similar process is actually applied to the stress calculations in our plane trusses element as well. So the normal stress in the plane trusses were first viewed in the local coordinate system, which is given by sigma, which is referred to the normal stress equal to E multiplied by B multiplied by Q. If we can remember from the previous lectures that from the calculated displacement, we will first allow to obtain the normal strain, and from this normal strain, which is we will use these normal strain information in order to obtain the normal stress, which this is equal to BQ, and the normal stress equal to E strain and equal to E be Q. For a plane trusses problem, this equation for the normal stress has first to be written in the local coordinate system. And after that, we apply the transformations from the local coordinate system into the global coordinate system by replacing the terms of the Q prime by LQ in the stress equations. So this is actually our Q primes. If we substitute this, then we finally actually will obtain this equation for the normal stress. And again, as we can see here, our normal stress for each plane trusses elements will depend on the L and M, which is requires the angles of the inclinations angle of our elements.